So hopefully it's recording now. It probably asked you for permission. Yeah, so today's topic is something which is often called contextual word embeddings. In practice, it actually means, yeah, we'll talk about BERT and multilingual BERT. Um, I'll first talk about what contextual embeddings are. So we had static embeddings before. They were just called word embeddings. And when contextual embeddings came, then they were retronamed static embeddings. So I'll briefly go over Elmo, and then we'll spend more time with BERT and mBERT, which also we will play with in the practicals. And we will especially be interested in multilingual properties of BERT, or especially of multilingual BERT, because it seems that it's very nicely multilingual, even though it's not trained to be. So last week we saw if you have monolingual embeddings, how to transfer them and map them so that they would work multilingually. And today we'll basically show that, well, with multilingual BERT, you typically don't even have to do the mapping. Uh, so, uh, so this is just a recap from last week, kind of. So if you have these static embeddings, so they are so-called type level. So for each word, you have just one embedding based on a fixed dictionary. So it doesn't depend on the immediate context. Well, it does depend on the context in which the word appears in the corpus. Of course, this is how the embeddings are computed. But in the given sentence, it doesn't take the context into account. So if you have these sentences, like I can train you to drink Coke, or I found a can of Coke on train, so then you have the words can and train in both of the sentences, meaning something very different and actually being a different part of speech. But the standard static embeddings just have the same representation for the words here. So uh, so this is definitely some kind of shortcoming, but of course there are other. So it does ignore the homonymy, polysemy, and similar phenomena. But the benefits are that they are really fast to use, to compute, because they're fixed, and they can be mapped bilingually. So this is what the previous assignment actually is. These are some good things. And yeah, I have here an example from the projector on the TensorFlow, which I showed last week, and uh, the example is interesting with showing some modal verbs, basically, or auxiliary verbs, and some months, and you will notice that the month May is not part of the cloud of the other months, so it's not very close to the other months because, well, it's also can be understood as a verb. But on the other hand, what you can typically expect is that uh, the verbs appear somewhere in some kind of cloud, and this one will be an outlier even for this one. So it's kind of an average embedding between these two representations. And depending on which of the meanings is more frequent in the corpus, then this will be closer to one or the other cloud. So I also have you can list the nearest neighbors for each of the words. So for January, you do see the other months, which is nice, and then some other things that have to do with dates. For the verb can, you do see some other verbs like can or cannot as the closest one. So we can already see that the meaning of can being a container for drinks or whatever is not very frequent in the corpus because these neighbors are mostly verbs. And for the verb may, for the word may, so we do see that the closest words are actually verbs. But also, if we look down, so we do see June here, we do see August here. So uh, both of the meanings are kind of captured in the embedding. Uh, so the distance between May and June is also reasonably small, but not as small as between June and July. So that's that's one of a problem or property of static word embeddings. And there have been some approaches to kind of disambiguate that, but mostly this has not caught up very well. So the actual solution that nowadays is typically used when you want to take the immediate context into account is using contextual embeddings, which are token level. So this means, So this means that for each sentence, the same word will have a slightly different representation. So if we got the contextual embeddings for these two sentences, so they should show that there are actually two different meanings of the words. Of course, this means that they're slower to use. They have to be computed for each sentence. So it's well more demanding to use contextual embeddings than static embeddings, and you cannot easily map them because they are different for each context. But they still, like, for a word with a fixed meaning, the contextual embeddings will still be very similar in different contexts of the word, because they still mostly capture kind of the identity of the word in some sense, or the word sense or whatever. But you can recover the local context from it to some extent. So it depends on the neighboring word, and it also kind of contains some information about the global context. So some sentence level stuff. So depending on how good the representation is. But this actually means interesting stuff for us. And this, for example, means that you can use them easily to do part of speech tagging. So we've already mentioned the option to do part of speech tagging with static embeddings. But I warned you that there is the problem that, the part of speech can depend on the immediate context, which the static embeddings cannot take into account. But here, you can just use the contextual embedding as it is and just train a classifier on the contextual embeddings independent of context, because the context is already encoded in the contextual embeddings. This is actually the assignment that you will have from today, to train part of speech taker on contextual embeddings, and actually a multilingual part of speech taker, because, well, why not? We are interested in multilinguality. There is one image from a paper that actually tried to link together static and contextual embeddings, and the example is that it's English and Spanish, because I guess some of the elders are Spanish. So you have the English word bear, which actually has two meanings. So one meaning of bear is the animal, and the other meaning of bear is kind of to hold something, or to, it's similar to hold, so as a verb. And in Spanish, these two meanings are different. So the verb would be tener, and the animal would be oso. So the visualization shows that for this star is kind of the average of all the English embeddings for bear, and the dots they show the kind of the two clouds of the two meanings of bear in English. So these are, I think this is multilingual BERT. So we do have representations for bear in different contexts. So we can see that it breaks down into the two clusters, kind of. So we can see that bear in English actually does have two meanings, and that they are clustered together. And then we can see the triangles are other animals in English, so we can see that this is the animal meaning. And we also do see the multilingual BERT representation for Spanish also, which also means bear as the animal. And I think this is the average of all embeddings, of all contextual embeddings of the word. So we can see that this is close to the English bear as an animal, whereas this is the Spanish tener, so the verb bear. And we can see that it is similar to the English bear in the meaning of a verb. So basically what I want to show is that, yeah, the good thing is that the embeddings encode both the word identity and the meaning in the context, as shown here. So where do we get the embeddings? So one of the first approaches that uh, kind of came up with the idea of contextual embeddings were Elmo. There was something before, but Elmo was the one that became widely used. So it's just a reasonably simple neural network that takes the static embeddings as the input and processes them with a bidirectional LSTM network. So yeah, if you know neural networks, then this is easy to understand. If not, then just the main idea is that you have the embedding of each word on the input, and then you have a recurrent unit that goes from left to right over all the input words, so that when you have the representation of the last word, it's informed by all the previous words in the sentence. And it's bidirectional, so you also go the other way around. So you start at the end, you go to the beginning. So each word is informed by all the words after it. And then you concatenate these representations, which means that for each word, you have a representation that contains the information about the word itself, but also the information about all the preceding words and information about all the following words combined using a neural network. So you could think up a simpler thing like, yeah, let's take the word and average it with all the other words weighted somehow. And basically, this is what it does, just in a more clever way. So you get information about the word. Um, this network is pretty simple, so it's something that's pretty easy to train yourself on a corpus. Um, and well, it's now people mostly use newer models, but this still works fine. And if you need to train something yourself quickly, then Elmo is better than BERT because it's faster to train. Now, what people typically use today, well, people move to other models, but a lot of most language models, most narrow language models these days are based on the transformer self-attention network. So in Elmo, it just went left to right and right to left, and then you would join it. And in the transformers, it just goes all the directions at once. So to get a representation of each word, there is a kind of weighted average over all of the input words. And again, this is trained and it's somehow clever, but the main idea is that, yeah, you combine all the information at once, so it doesn't have this kind of directionality. It can easily focus on the important words in the context, independent on where they are located in the sentence. And in fact, it has multiple layers. There are different variants that you can use. So in BERT, I don't know if it's something like 16 layers of the transformer, so that all the information about all the words gets combined into the word representations on one layer. And then again, there is another layer that again recombines the information in some way. And this goes on for maybe 16 times. So at the end, you get representations that kind of uh, take into account all the words in some sense. And uh, you can train this yourself. It's some kind of computationally demanding. So typically what people do is that they use some pre-trained models that have been trained on some large text corpora. There are some interesting properties that you might be also interested in, and actually Tomasz could talk more about this. So one thing is that because there are multiple layers, so the findings are that the different layers tend to learn different linguistic properties, or how to say. So the initial layers, they typically learn something about morphology. So from the initial representations, you could extract some information about morphology, and then the further layers, they seem to learn also something about syntax. So from the further representations, you could extract even some information about, well, syntactic properties of the words, which might make sense if you're trying to do syntactic parsing, to know into which layers to look at. But basically, the two common approaches that people do is either take only the final representations, so from the final layer, and saying, yeah, so this has taken into account most of the stuff, or they actually do use all the representations from all the layers, and maybe they weight them somehow. But in the practicals, we will just use the last layer. So there are the words that come in as static, and then they are remixed many times, and then something comes out which corresponds to the words in their context. Um, what BERT also does is that it starts the sentence with a special token, CLS, which is meant to be used if you want to do some sentence level stuff. So, for example, classifying the sentences, so that you get an embedding of the whole sentence, kind of. It has been shown that it's sometimes useful, but sometimes it's just better to do an average of all the words in the sentence, and you get a better sentence representation than from the CLS token. So this depends on what you want to do. And actually, yeah, the image here actually is lying a bit. So in fact, you don't get representations for the full words. Sometimes you do, but the words are tokenized by splitting them into subwords called word pieces, I think, for transformers. So if the word is not some short common word, so I would guess in this case, probably sesam would be split into multiple pieces. So we get representations, so contextual embeddings for the pieces of the word, and then it's up to you whether this is okay or whether you need to combine them together. And typically you would just sum them up, or compute an average of the embeddings for the individual pieces, and say, yeah, the embedding of the whole word is just the average of the pieces of the word. And yeah, so this way you get some useful representations of the words. And yeah, there are some fun properties of the training process, that even the training is not linear, like going left to right to predict the next word, which is usually what language models do, but it's also kind of skipping around. So when you train it, you just mask some of the words, which means you kind of delete some of the words from the input, and you train the network to predict the missing words. So it does not have these directionality issues that arise. So it shouldn't have trouble with languages with weird word order and stuff. But as I said, it's costly to train it, so usually you just download pre-trained models. Um, the good thing is that already, well, kind of from the beginning of BERT, a multilingual model has been also made available. So typically, a lot of the models are just on English, but there also exists something called multilingual BERT. Usually, people shorten it to mBERT, which has been trained on 104 languages. For some languages, this was Wikipedia texts. For some languages, I think there were more texts added than just Wikipedia. I don't actually know the details. And the interesting thing that we will look at is that actually, well, this works good for each of the languages separately, but also surprisingly, it works fine even across the languages or when processing multilingual data. Uh, if this is the mBERT is not what you're looking for, then there are even some other versions. There is something called Slavic BERT, and very recently there is even something called CERT, which is BERT trained on Czech data. So there are other options as well, but in the practicals we'll work with BERT in English and with mBERT. And well, people have been asking how multilingual is it? So because it was trained just on a kind of a concatenation of multiple languages, so there is no guarantee that the representations are in any way bilingual or cross-lingual, unlike VecMap, which explicitly maps the vectors onto each other. But it has been found that actually the mBERT embeddings are highly multilingual, and often they are even better than VecMap in their cross-linguality. So what this means that they are multilingual or cross-lingual, how to call it. So what I mean by that is that similar words have similar vectors not only within the language but also across languages. So if you had the word for dog in English, and Czech it would be pes, and in other languages it would be other words. So it's very likely that their mBERT representations will be actually quite similar. Um, so uh, so this makes mBERT actually very useful for, well, any cross-lingual experiments. Uh, and the same is not true not only for the meanings of the word, kind of the lexical meanings, but also for like linguistic properties. So if you're interested, for example, for in predicting part of speech, which you will be in the assignment, then again, the uh, mBERT embeddings seem to capture part of speech in a similar way across languages. So it means if you take contextual embeddings from mBERT for, let's say, English, and you train a part of speech tagger to predict part of speech from the embedding, just using something simple. I will be showing how to do it with MLP classifier. Then you can directly apply this tagger to a different language. So you take, I don't know, Czech language, and you convert the text to mBERT contextual embeddings, and you apply the classifier. And typically this would work, well, pretty well. You will see when you try this out at home. So you don't have to do any mapping, you don't have to do any transformations, you don't have to do any fine tuning, and it works. Like it works better if you still do some of this stuff, like fine tune it a bit, but the strength is that you can just use it directly. You can just download it, run it, and it will do something which won't be too bad. Um, there is another work that analyzed it a bit more. And so this was done by Jindra Libovický, mostly from UFAL. And what he found is that actually the embeddings, the contextual embeddings, they can be kind of factored into several pieces. So they seem to be like a sum of several pieces of information. And so you can try to extract actually the language identity from them. So what this experiment showed was that if you take, for example, all the languages in what we have here, Sundanese. Okay, we have all the sentences in Sundanese that we have in our corpus. We compute their mBERT embeddings and average them together, and we have this as one kind of language embedding, we can say. So this is an embedding of all the words in the language that we've had in our corpus. So this is one vector, and then we take all sentences in, I don't know, in Farsi, and do the same thing, and we get an embedding for Farsi. And this is a visualization of the embeddings, again, projected to 2D using, I don't know, PCA or TSNE or something. Uh, so what you can see is that actually languages from similar language families tend to have similar embeddings. So for example, here we have some Germanic languages, and we can see that the similarities of their embeddings make some sense. So if you average all the words in German and all the words in Dutch, then the averages will be very similar and quite different to maybe all words in Slovak. So this means that uh, the identity of the language is somehow encoded in the embedding. By the way, it's state of the art for language identification. So somewhere at the beginning, we had the LangID library to identify languages, and using mBERT in this way beats it a bit. Well, the library is also already very good, so there is not much space for improvement, but this one turned out to be slightly better. And this means that when you do have the language identity as this kind of language centroid, so the language embedding, so you can just use plain subtraction to remove the language identity from the embedding, and what you get is some kind of representation which is more language neutral. So it kind of moves all the representations towards, let's say, the center or something. So that the representations are more language neutral, meaning more cross-lingual, in fact. So that's one of the operations that you can try to do. But you don't have to definitely in the assignment. It's not definitely necessary to do something like that. It's just an interesting property if you really need the representations to not to possibly encode the language. They still encode the language, but weaker. And one piece of work by Dan Kondratyuk, which was, I think it was a student of Milan Straka. And I think he got some award for this work. It was his master thesis. The obvious idea is, okay, so we have, at this time, there were 75 languages in UD. It's like 2 years ago. And the idea was, okay, so if mBERT gives us this multilingual embeddings, so we can probably just train only one syntactic parser for all the languages in UD if we run them through BERT, for mBERT actually, to get some multilingual representations. And this turned out to be a great idea and had really great results uh, in basically for all cases that it was evaluated for. So it works easily. So you take the sentence, you get the mBERT representations, and then you can predict various annotations. So part of speech or features or lemmas or dependency structures, just independently, actually, mostly. And then yeah, there was some improvements. So here there was something called layer attention. So this is what I mentioned. So you might take just the last layer, but here what Dan Kondratyuk did was to take all the layers, but to train some kind of layer attention. This means which weight to give to each of the layers for the specific task. So taking into account the fact that maybe for predicting part of speech, you would want to focus on the initial layers and so on. Uh, he also got some improvements by actually fine-tuning the BERT for the task. So it's trained for a different task for predicting words. So you can just use the whole training data to still uh, fine-tune BERT. This means to keep training it for something else so that it specializes for this task, so the representations better capture some morphological and syntactic features. So this kind of gets rid of uh, some limitations of the previous approaches that we've seen. So so we had delexicalized parsing, and well, it's similar to that. So it has some approach that you can have one delexicalized model to apply to any language, but here you first need to have part of speech for the language, and you cannot take the word identities into account. And we've seen the static embeddings, which you can map multilingually. So you can get rid of some of the limitations, but they are still not contextual, and you have to do some extra work. And with mBERT, you get beyond the static embedding. So they're not static anymore, they are contextual already. And you don't have to do any mapping because they're multilingual just by themselves. And you don't need to have part of speech for the languages because, well, if you have part of speech for one of the languages, so you just trained part of speech tagger for one language and then use it for the other languages. So it's fairly simple to do. And it's not only simple to do, but it also has great results. So uh, for the large languages, so you train one model, so it's also trained for Czech, English, these languages with large tree banks. So it typically does not surpass the parsers for the languages, but sometimes it does, and at least it's always competitive. It seems that even like training a parser on Czech and Slovak data is better than training on just Czech data because the similar languages can also inform the parser. And for lower source languages, well, I don't know if it's still state of the art today. It was state of the art 2 years ago, but at the time it was definitely state of the art. So if you had few data for a language, then this would work really well, and even for no resource languages. So this is something called zero shot parsing typically, or zero shot whatever, that you don't even train it for the language. So you train it for English and Slovak and Czech, and then you apply it to Swahili and it still works fine. There are some results that even show that even for languages that mBERT does not, it was not trained on, then it works somehow, but usually not very good anymore unless it's similar to one of the languages. So typically you would still want one of these 104 languages that mBERT was trained for. But otherwise, yeah, you don't need any data, any other data than plain text for that language. Um, so yeah, this kind of uh, replaced most of the approaches that we've seen before because it's easier to do, more universal. You have just one model for everything. And yeah, so uh, I would say typically when you want to do something multilingual, then using multilingual BERT is a good first thing to think about whether it makes sense. It might not make sense if, well, it wasn't trained for that particular language, for example, or if you don't want to use embedding approaches, but you need to, for example, look at the individual letters or something. So yeah, it's not a golden bullet or silver bullet for everything, but very often it will lead to the best results. So it's worth knowing about it and well, being able to use it at least a bit. So so that was the lecture part. So uh, we we have a lecture on contextual embeddings, which are better than static embeddings by the thing that they capture context, and they are kind of disambiguated word senses. We've looked at Elmo and especially BERT and especially mBERT or multilingual BERT, and we'll now play with mBERT in the practicals.